Okay, folks. So let's go ahead and get started. It looks like most of you are able to get the work done, get the lecture. You're able to watch the lecture and get the problems done in time. I'm still, I'm in the process of trying to refine things, trying to make sure that I can present the video enough information during the course of the video without making it too long and giving you enough time to make sure that you can finish it within the period of our class. It's still a work in progress. I think I'm getting there. And so what'll happen is I'm going to try to shoot again for that 25-minute mark, maybe a little bit less, because like I said, a few of you are still having some issues with finishing on time. Again, if you're having an issue, if you're having a hard time finishing the video, then just let me know. What I would suggest you do though, folks, is make sure that as soon as you check in through Google Classroom, make sure you just enter here for the attendance for the day. As soon as that's done, go ahead and start watching the video. I do time it so that if you start the video at the very beginning of class, you should be able to finish with everything at the end of class. I was following the progress of a few of you guys as you were watching the video, and some of you were starting a little bit later than the actual start time of a period. If that's the case, then obviously you'll run over time, and you won't be able to finish the video and the lecture before your next period starts. And so you guys make sure as soon as you check in, start watching the video and get it done. My hope is that we can get to the point where I'm presenting you the video with enough time to watch and get the work done. At that point, then I will have to be a little bit more strict with the deadlines. But until we get to that point, try your best with it. But if something does come up, like I said, let me know, and then we'll work something out. But again, like I said, as I was kind of watching your progress this morning. A few of you were waiting a little bit longer than you should to start the video. Folks, please make sure as soon as you check in, make sure you get to Edpuzzle, start watching the video right away. Okay. I haven't seen anyone stop by after school yet for our Zoom tutorial sessions. Please make sure you take advantage of that. If there's any questions about these calculations that we've been doing, these stoichiometric calculations that we've been doing, um, come on by. I will, it's a live session, so I'll work those problems out for you. Your homework, so I'll assign set B for chapter 12 today. So your homework over the weekend will be to practice doing the stoichiometric calculations here. And then, like I said, if there's anything you don't get, please make sure you come by and see me. The math, I think, is pretty straightforward. We'll practice it some more here in just a moment. I'll introduce a couple of more calculations, stoichiometric calculations, and my hope then is on Monday we'll be able to get started with the discussion of limiting reagents. In terms of quizzes and possibly exams, I have an idea of what we could possibly do for that. I will, as we get closer to the point where we will be taking a quiz or possibly an exam, I'll let you know how it'll be done. I won't be giving any pop quizzes. I will announce the quizzes for you, and I will lay out the procedures for you and on how we will do the quizzes. Okay, but I'll let you know about that next week. Okay. Also, I'd like us to do a PhET lab next week, and that PhET lab will take the place of a lecture. I'll let you know which PhET lab we're going to be doing and when we'll be doing it, but I'll give you that information next week. Okay. All right. So I think that's it in terms of the announcements. Again, you guys have been doing a good job of turning in the lecture material and turning in what I'm asking for. Also, just please make sure you check in. Don't forget to check in, and then start the Edpuzzle. Okay. All right. I'm going to ask you to do this here. Obviously, the importance of coming up with the right formulas is it can't be downplayed. especially for what we have to do, especially when we're using the molar masses where we need the correct formulas. And so what I'd like to start out with today is number 3 in your problem set. Okay, what I'd like you to do is take these compounds here, and for the first 2, give me the formula, and for the second 2, write down the names of those compounds. Take about a minute to do this, okay, and then when you get back, I will go ahead then and I will give you the answer. Make sure you write them down. But then again, the whole point beyond this is if you're not getting the right answers here, please make sure then that you practice it and then combine save me. Okay. All right. So go ahead and get it done, and then I will give you the answers in about a minute. Okay. Okay. Let's take a look at these 4 compounds here, and let's name them. Write down the formulas for the first 2, and then name the second 2. I think of the 4, I think being able to come up with the formulas is going to be fairly important. Okay, so ionic compounds for both these metals and non-metals in both cases. The cation here is going to be potassium. Chromate is going to be Cr, potassium's K plus. Chromate is going to be CrO4 2 minus, and so our formula then is going to be K2 CrO4. Okay, make sure if you're not quite, again, you just got to memorize the polyatomic anions, folks. There's no getting around that. Okay, so make sure you memorize polyatomic ions and then write those down. Okay, sodium hydrogen carbonate, then it's going to be Na. Okay, again, it's not a binary compound, polyatomic ion here, anion, that's going to be HCO3. Okay. All right, so that's the formulas for those 2. It's important that we get the formulas here in order to get the correct molar masses. Okay. All right, so the next one then, I will give you this one. This is an acid here. There's your cation. Okay, remember with acids, we used acids quite a bit in the last chapter, but we'll learn more about acids in chapter 19. But acids are ionic compounds in which the cation is going to be the hydrogen, and the anion is going to be either a monatomic ion or a polyatomic. This is polyatomic. We have certain rules that we will learn to name acids. So I'll go ahead and give you this one here. This is known as permanganic acid. Okay. And there are rules that we use to help us name these, and we'll learn these rules when we get to the chapter on acids. Okay. All right, and for the last one though, you should be able to name it metal or non-metal. Hopefully you recognize this potassium. Okay, and the anion then is the oxalate anion. Potassium oxalate. Okay. All right. So if you weren't able to, I didn't really expect you to be able to get the permanganic acid here. That we haven't learned yet, but if you got it, good for you. But with the other 3, hopefully you were able to get that. Okay. All right. Let's go ahead then and let's quickly review where we left off with yesterday. We were talking about how we want to be able to obtain the masses, so of the compounds or the substances that are involved in a chemical reaction. So if you're given the mass of one of the components of the reaction, the goal then is that we need to try to get the mass of a second component of the reaction itself. So if we know the mass of one of the components of the reaction, we should be able to get the mass of the second component of the reaction and using a conversion. Okay. The only problem that we have here then, folks, is that there are no conversion factors that we've learned about so far that allows us to do directly a mass-to-mass calculation. Okay, so that's not possible for us. And so what we have to do then is that we have to kind of go in a roundabout way in order to do this conversion right here. So we have to go a roundabout way to get this conversion done. What we can do though, and we talked about this, is that if we know the moles of the first component of the reaction, and we want to find the moles of the second component of the reaction, okay, we can do that because there is a conversion factor that allows us to go from moles of one component of the reaction to moles of the second component of the reaction. That is the mole ratio. Okay, so once we have that, so we have a way to get from moles, not mass, but moles of one component of the reaction to moles of the second component of the reaction. Okay, the only problem is, how do we bridge this gap here? Okay, that is, how do we find out the moles of this compound? Because what we know then is we know the mass. So again, we know what the mass is of the component. Okay, but how do we get the moles? Because we can do this conversion here. We can't do that conversion, but we can do this. So we need to be able to convert this mass here that we do know. So this is what you're known. So that's what we were given. That's the known. Okay. How do we get from there to the moles of that compound? Well, we did that conversion back in chapter 10. That was a molar mass conversion. We needed the molar mass in order to get that done. Okay, so understand this. The conversion that we're doing here is going to be a grams to moles conversion. And if you remember, in order to do that, then we would have to divide by the molar mass. So the very first step, it requires that we divide by the molar mass in order to get the moles of this known mass here, and the moles of this known component of the reaction. Okay. All right. Once we have the moles, then we just use to plug in the mole ratio between the first compound and the second compound. Okay, and we get the moles of the second one. So therefore, again, we don't want the moles here. Okay, if we are asked to find the mass of the second one, and this is our unknown, the question is, if we know the moles of the unknown, can we then find, can we then find the mass of the unknown? And again, that we can do because this is a moles to mass. Okay? This is going to be a moles to mass conversion. And we know then in that case, then if we multiply by the molar mass, okay, so here we would multiply by the molar mass, we would get our final answer. Okay, so this, folks, is stoichiometry. Okay. All right, so with that said, then I asked you to do this problem here. We left off with this problem here. I asked you to do it yesterday. So what I would like to do is I want to go ahead and work out this problem for you now. Okay, and let's go ahead and let's take a look at it. Okay. All right, so we start out, we got to get the balanced equation. Okay, so the reaction, the problem describes for us the formation of rust, which is iron 3 oxide from iron and oxygen. Okay, so let's go ahead and write down the balanced equation first. Okay, so we have then iron in the solid state reacting with oxygen in the gaseous state to produce for us iron 3 oxide as a solid. There's our rust. Okay. All right. So let's go ahead. Always make sure you balance the equation first. All of stoichiometry requires that we balance the reaction itself. Okay, so we write this in. It's going to be 4, and make sure you get this, folks. If you're not quite sure how we get this, make sure you stop by after school today and ask 4, 3, and 2 will give us the balanced equation. Okay. All right. So at this point, then what I typically do is I'm going to go ahead. Remember, this is a conversion. Remember, stoichiometry is this one long conversion. What I do then is I identify what we start out with. So in the problem itself, then we are told then that we are starting out with 12 grams of iron. Okay, so it tells us then how many grams of rust are produced when 12 grams of iron rust. So we're told then that 12 grams. Okay, we have 12 grams of iron metal, and we're trying to find then the conversion then is to the mass of iron 3 oxide. They're trying to find, they want us to find then the grams of rust that forms the mass of rust. Okay, so if you see then that's our conversion. It's a conversion between this component of the reaction to this component of the reaction. So once we've identified what the conversion is, okay, what we start out with and what we want to end up with, let's go and set it up. Okay. So again, this ends up being a conversion very much like the ones we've done in the past in chapter 3 and in chapter 10. You start out, you ask yourself, what do you start out with? What do you want to end up with? And what are the conversion factors? So let's go ahead and set up our problem. So we have 12 grams of iron, okay? And we want to solve for the mass of iron 3 oxide of our rust. All right, so we have to identify the conversion factors that will get us from start to finish here. Okay? Well, we said then from the schematic, from the flow chart that I gave you in the previous slide, we can't do this directly. There is no one conversion factor that will get us from grams of iron to grams of iron 3 oxide. We saw then that there has to be 3 of them. Okay? And so the very first one we saw then was the molar mass of iron. And we'll go ahead and write this down then. It's going to be 1 mole of iron for every 56 grams of iron. So there it is. There's the first relationship. There's the grams of iron that we need. That'll cancel out that one. Okay. However, we need to get the grams of iron 3 oxide. That's not going to, this one conversion factor will not get us there. As you notice, you don't see grams of iron 3 oxide in either one of these here. So we have to continue on. Okay. All right. Second conversion factor that we needed was the mole fraction. Now, here was our molar mass. Okay, so there's our molar mass. Okay, the very first one that we need. Okay, and you're going to see then as you continue to do more and more of these problems, it becomes very simple because you're going to be using essentially the same process to solve most of these problems. Now you have to be careful with that. They're going to be, you still have to ask yourself 3 questions because there may be some variations in what you have to do here, but essentially this is the process you're going to be doing. Okay. All right. So the next step then is we're going to identify the relationship between iron and iron 3 oxide, and that's your mole ratio. Okay. So therefore then we have 4 moles of iron, and again this is taken straight from the from the balance equation. For every 2 moles of iron 3 oxide, and there it is. Now we have moles of iron, but and then there is our iron 3 oxide. Okay, unfortunately this is moles of iron 3 oxide, and we need the mass of iron 3 oxide, and so therefore we need one last conversion factor to get so this is our mole ratio. We need one last conversion factor to get us from moles of iron 3 oxide the grams of iron 3 oxide. We know what that is. That's going to be our molar mass. Okay, so the molar mass of iron 3 oxide, the moles of 1 mole of iron 3 oxide, and you add all those up, you're going to end up with 160 grams of iron 3 oxide. So there is our second molar mass, and there are the 3 conversion factors that we need. And if you notice, if you take a look at these 3 conversion factors here, there is our starting amount and starting unit, grams of iron, and here's our final unit, grams of iron 3 oxide. So in these 3 conversion factors here, we have the 2 quantities that we identified here at the top. Okay. All right, let's go ahead and plug it in. Let's solve for it, folks. All right, so our very first conversion factor, again, has to be able to take care of this unit, grams of iron. This is the only conversion factor that has grams of iron in it, so we're going to use that first. We're going to plug it in with moles of iron on top and 56 grams of iron on the bottom. Why? Because that allows us to cancel out that unit. Okay, so we are done with this conversion factor. Remember, once you've used one conversion factor, don't use it again. Okay, all right. So we have now moles of iron. We want to get to grams of iron 3 oxide. Okay, so the only of the 2 conversion factors that are left, the second one has moles of iron in it. So we're going to use that one. Okay, so we'll plug that one in. This time we're going to plug 2 moles of iron Fe2O3 on top and 4 moles of iron on the bottom. Again, why? That allows us to cancel that unit. Right, so once we're done with this conversion factor, don't use it again. Okay. At this point, we're not done yet, folks. Right now, on the left-hand side of the arrow, we have moles of iron 3 oxide, and on the right, we have grams. And so we need to use that last conversion factor, okay, in order to solve for grams, okay, in order to cancel out that unit. And we're going to plug this in then as 160 grams of Fe2O3 over 1 mole of Fe2O3. And that allows us to cancel out that unit of moles. And there it is. Now we have, I'm sorry, now that we've used that one, you see that we have grams of iron 3 oxide on the left side of the arrow and grams of iron 3 oxide on the right side of the arrow. The unit analysis is done. We just have to plug in our numbers and we'll get the number here. But before we do, I just want to point out to you again, hopefully you noticed it, the very first molar mass here, we divided by the molar mass. The mass was on the bottom. So we divided by the molar mass here. Okay, there's our mole ratio. And then we multiplied by the molar mass, the new molar mass here. So you divide and you multiply. And if you notice, that's what we saw on the flow chart that I gave in the previous slide. So you plug those numbers in, you'll come up with your answer then is 17 grams of iron 3 oxide, 2 sig figs here, because we started out with 2 sig figs here. So make sure you are mindful of the significant figures, okay? All right, very good. I'm going to ask you then. Let's go ahead. I'd like you to do. Okay, so let's go ahead and let's continue on. There are other stoichiometric calculations we can do. We saw that mass to mass conversion, but since we know that the mole is also related to the volume and number of representative particles as well. Remember that Avogadro's number and the molar volume. Okay, so because of that, then if we know what representative particles, how many we start out with for a particular reaction, we can find out the number of representative particles for any other component of that reaction. Okay, so we can do other stoichiometric calculations as well, okay, because we know what the relationship is between moles and mass, moles and volume, and moles and Avogadro's number. Okay, and so it all starts again with identifying the coefficients, using that to get the mole ratios, and then making sure then that you ask yourself, what do you start out with, and what do you want to end up with to finish it out? Okay, so keep this in mind. These were the um, 4 conversions that we did back in chapter 10. We're going to take advantage of these 3 here. We're not going to do this one so much in this chapter, okay? But we're going to take advantage of the relationship here between moles and particles. We already did moles and mass, okay? And then we're going to use moles and volume to do our stoichiometry, okay? All right. Basic idea then is when we do this, make sure you get the balance equation. Okay? You want to identify the starting unit, and basically what I'm doing here is I'm going to highlight for you all the steps that you have to go through to do these do these calculations. Don't memorize them. You'll learn them by doing. Okay, but essentially then you're going to ask yourself 3 questions. 3 questions. And after you get the balance equation, what do you start out with? What do you want to end up with? And then make sure you identify the conversion factors that you will need in order to get the conversion done. Okay, you plug them in, making sure then that you set it up so that you cancel out the unit that you start out with, and that you end up with the unit that you want. Okay, and then you multiply or divide the numbers. You multiply and divide the numbers, and then you'll get your final answer. Okay, all right. So let's go ahead and take a look at an example here. Okay, let's look at this flow chart here again. This will be our known. Let's say you were given a problem where you were given the mass of one part of the reaction. So this is what we know. Okay, this is the known quantity. And we want to find then, say, number of particles of another component of the reaction. Okay, and there is no conversion factor that gets us straight from mass to number of particles. So we can't do that directly. There are no conversion factors that we've learned about or that are available to us that will get us directly from mass to number of particles. However, again, if we can get the moles of the compound 1, okay, and if we know what the mole ratio is, we can find the moles of the second component here. Okay, so the question is, can we get from mass to moles? Absolutely. We use the molar mass again, and again, what you're going to notice is we're going to divide by the molar mass initially here. Okay, so we'll do that. Then we get to the moles here, use our mole ratio. To get our final number of particles, do we have a way to get from moles to particles? Moles to particles? Absolutely. Avogadro's number. And we'll plug it in, and you'll notice here then we will multiply by Avogadro's number in this case. Okay, so the process then again, folks, is very similar, almost identical to what we did with the mass to mass conversion here. Okay. All right, so let's take a look at an example here and work through a problem together. Okay. And then I'm going to ask you to practice the problem as well. All right, so we have then, we want to find then the number of molecules of oxygen, okay, that are produced. So when water is decomposed. Okay? So we're talking about the decomposition of water. So the very first thing we want to do is write out a balanced equation. If it's decomposition of water, we start out with water, okay, on the right-hand side. This is a binary compound, so therefore we end up with the elements, okay, of that makes up the compound. All right, and so when we balance this, then again, make sure you combine C and B. If you're not quite sure, we get this can be 2, 2, 1, and that'll be the balance equation for this particular reaction. Okay. All right, so let's go ahead. Oh, sorry. Let's go ahead then and let's write down what we know, what we are given, and what we are solving for. Okay, so underneath the balance equation, we are told then that we have 29.2 grams of water. That is our known. So let's go ahead and write that in. So we have 29.2 grams. That's what we know. What are we solving for? We're solving for oxygen. So we're solving here for oxygen. That's our conversion, but not grams of oxygen here. We're asked to find the molecules of oxygen. Okay, so how many particles of oxygen, how many molecules of oxygen is going to be produced? Okay, that's our conversion right there. This is what we start out with. That's what we're going to solve for. How do we solve for it? Okay, so let's go ahead and let's work this one out. Okay, so let's go ahead. So we're starting out with 29.2 grams of water, and we want to solve for the molecules of oxygen. Okay, so again, from the flow chart that we saw up, in the previous slide, there's not one conversion factor that will get us from the mass here to number of particles. So we have to string together a few of them. Okay. Well, we know the molar mass here first is what we'll need from that flow chart. You saw then that the molar mass is what we'll use first, and that's going to be the molar mass of water, which is 1 mole of water, and the molar mass of water is going to be 18 grams of water. So use those flow charts to help you study, folks. Make sure you use to help you do your homework and help you study. But then we're going to use the molar mass here first. Okay, and remember from that slide, what did we have to do? We had to divide. You divide by the molar mass. Okay. The second conversion factor from that flow chart then is going to be the mole ratio. And the mole ratio here is going to be between water and oxygen. So we'll write that down. It's going to be 2 moles of water, and that's why we need the balance equation for every 1 mole of oxygen. Okay, and then finally here, we want molecules. In the previous problems that we did, calculations we did, we wanted to end up with grams, and so we had to use the molar mass then. But here we want to use the molecules then. So therefore, the conversion factor we're going to use then is not the molar mass, but we're going to use Avogadro's numbers, 6.02 times 10 to the 23rd molecules of oxygen. We'll write it then as 6.02 times 10 to the 23rd O2. Okay, then this is then Avogadro's number. Okay, so that's what we will use, and what we said then is we're going to multiply by Avogadro's number, and you're going to see it work out that way in a moment. Okay, so let's go ahead. Let's plug in our conversion factors. Okay, so very first one, we're going to use the molar mass. We're going to go ahead then, we're going to write divide by the molar mass, so we saw there, so it's going to be 1 mole of oxygen over 18 grams of oxygen. Why do we do it that way? Because that unit cancels out. Okay, molar mass is next. Okay. Okay, well, and so we're going to go ahead then, and we're going to have moles of oxygen on top. Why? Because we want to make sure that the moles of water here cancels out. So therefore, it'll be 2 moles of water on the bottom. That unit cancels out. And then finally here, we want to cancel out moles of oxygen. So therefore, we will multiply by Avogadro's number, which means then we'll be put that on top, 6.02 times 10 to the 23rd O2 particles. Sorry, you guys. My writing board is on the blitz a little bit. So, but that's Avogadro's number of O2 for every 1 mole of O2. Okay, and that cancels out there. We end up with molecules of O2 here, molecules of O2 on the right. Okay, you plug in your answer, you plug in these values into your calculator, then you end up with an answer of 4.88 times 10 to the 23rd molecules of oxygen. Okay. So read the problem carefully, folks. Again, identify what they give you, okay, what you start out with, identify what they want to solve for, find your conversion factors, plug it in, and solve for the problem. Okay. All right, so what I'd like you to do is let's take a look at number 18 in your problem set. And let's work out that problem, okay, and take about a minute to work out that problem. Set it up at least, set it up and do the best you can, and then take about a minute or two to work out the problem. And if you don't have the answer, at least try to set it up, and then I'll work it out for you. Okay, so let's go ahead and get started with this, and then and then I'll work it out for you. Okay, let's go ahead and let's take a look at number 18 in your problem set. Remember, always start out with the balance equation first. Okay, and so here they gave you an equation here. It's the decomposition of potassium chlorate. So we're told then that potassium chloride is KClO3, okay? And it decomposes to form potassium chloride, and they give that to you, KCl, and oxygen gas. Okay, so that's what we have. And so this equation is not balanced, so make sure you balance it first, folks. So the balance equation then it's going to be 2, 2, and 3. Okay, so that'll give us the balance equation. All right, so in the problem itself, and this, again, this is what I like to do. I always want to make sure I write out the what we're given and what we're solving for. So in the problem that we were told that we have 6.54 grams of potassium chloride. So we're told then that we start out with 6.54 grams of potassium chloride. And what they want us to do then is to find the conversion here, to find the amount of oxygen that forms, not in grams, but in molecules again. Molecules of oxygen. That's conversion that we want to do. Okay, so let's go ahead, let's do the conversion. Okay, so, and let's write this out. So we start out with 6.54 grams of KClO3, and we want to solve for then molecules of O2, and I'll just write it then as O2. Okay, all right. So the conversion factors that we need, let's go ahead and write those down. We know then that we need the molar mass. So it's going to be 1 mole of KClO3. It's going to be equal to, I have your 123 grams of KClO3. Okay. We need the mole ratio, the mole ratio between potassium chlorate and oxygen. That's going to be 2 moles of KClO3 for every 3 moles of O2. Okay, and then finally we need the Avogadro's number, which is going to relate 1 mole of oxygen. Avogadro's number, which is 6.02 times 10 to the 23rd oxygen molecules. And so now that we have the conversion factors, we'll go ahead and we'll plug them in. Okay, so first one then has to be moles of potassium chlorate. Let's go ahead and plug that in. We have then 1 mole. So we're going to divide by the molar mass, folks. 1 mole of KClO3 over 123 grams of KClO3. That allows that unit to cancel out that unit. Okay. Next conversion fact. So we're done with this one. Don't use it again. The second one then, we're going to use the mole ratio for the second one. And so therefore, we'll plug in moles of oxygen on top and moles of 2 moles of KClO3 on the bottom. Why? Because it allows us to cancel out that unit. Okay, and then finally, then I'm going to use Avogadro's number. Okay, 6.02 times 10 to the 23rd O2 particles for every 1 mole of O2, and that allows us to cancel out that unit. We have then molecules of O2 on the top on both sides. We plug in our numbers into your calculator, and you get your answer then is 4.82 times 10 to the 22nd O2 particles. And that is your answer, okay? All right, very good. What I'd like to, what I'm going to do there, I'm going to pause right there. We'll pick up with the last stoichiometric calculation. The lecture went a little bit longer than I wanted today, but that's okay. I wanted to make sure that I cover the 2 stoichiometric calculations that we've gone over so far. I give you a chance to practice that. I'm going to go ahead and I'm going to assign the set B for chapter 12 for you to do. Do the mass-to-mass conversions, do the mass to particles conversion. Go ahead and give the volume, this volume to volume calculation here. Go ahead and do that if you think you can. But if not, set that aside. I'll go over it with you on Monday. Remember, the homework won't be due until Monday night anyway. And so once we go over it, you're going to see then that this is the easiest of the 3 stoichiometric calculations that you'll have to do. Okay. All right, so I'll ask you to do a couple problems from your from the book, just as a chance to practice it, and then make sure you write down your answers on your paper, and make sure you turn it in by the end of the period. Okay, Have a good weekend, folks. I'll see you, and I will see you on Monday.